session. And Ritika, Pritam, Suman, Somajit. Okay, these people are there. Now, today I'm going to talk about something which is very important from the viewpoint of statistics. Okay, and so I'm going to start with a very basic question, and you are going to reply to me if I ask you any question regarding this issue. We all know that when we start studying probability theory, we deal with this particular problem. It's a very fundamental basic problem, and we are pretty much comfortable with it. And after that, when as the probability theory progresses, we say that, okay, we define many other events like independent events, mutually exclusive events. We define conditional probability Bayes theorem, etc. and etc. And we develop the probability laws, and then we could move on to probability distribution. Everything we do after that has already been discussed more or less in the class. But what is the basic objective? To understand the basic objective of all these things, of doing all these things, we have to go back to our basic coin tossing problem, okay, which is very fundamental. And with the help of the problem, I'm going to introduce something which is probably new to you, is a new concept. Probably you have not seen this concept earlier in any other courses. Now, in coin tossing problem, whenever we toss a coin, we know that we are left with a sample space which has two possible outcomes. One is H and another is T. Okay. And according to the sample space, if I ask what would be the probability for this event or this event, we accordingly say that, okay, probability of event H. Why am I writing it in this manner? It's because, if you can recall, event is actually a subset of sample space. So obviously, as you can see, that this event H is a subset of the sample space omega. This event T is a subset of the sample space omega, and omega is also a subset of the sample space omega itself, and so on. Okay, so to make things short, we simply don't consider this single element set in the manner it is written. We simply say that probability of H. Probability of H means probability of this particular set. That means probability of this event. And then we put the value. Similarly, for probability of tail, event tail, we denote simply by probability of T, and we put some values. Now, what are these values of probability of H and probability of T? What are these values? What probability do we have for head and tail to occur in an experiment? We say that the probability of let me not speak about it. Anybody, Ritika or Ritika, tell me what will be the probability of head and probability of tail?
So 1/2 and 1/2.
Yes, 1/2 and 1/2. But how do you get this particular probability? How did you calculate this probability? You calculated the probability by simply using the classical definition of probability. Probable number of cases by total number of cases. The question is, while I talked about the coin tossing problem, I never mentioned whether the coin is a biased coin or an unbiased coin. I never mentioned this. I don't know whether coin is unbiased or biased. Okay, I simply said that it is a coin tossing problem. What would be the probability of head and probability of tail? You said that this would be half and half only if the coin is unbiased. But what would happen if the coin is biased coin? Now the question is, what will be if the coin is biased? Coin is biased because there is no way by which we can immediately say by looking into the coin that it is an unbiased coin. Okay, this we cannot say. We cannot predict that the coin is an unbiased coin because there are many features which needs to be studied, and we are not sure about how many features should be studied to declare a coin to be unbiased. We simply know that there are some features which need to be studied, but how many features are there, how to study them? You are doing an experiment with a coin where in a room where the humidity is high, or suppose the air friction is very poor, or suppose the coin is broken, minutely broken on one side, which is not seen through a naked eye immediately, or maybe during the manufacturing of the coin is sort of heavier to the one end. There may be many reasons which need to be studied to declare that the coin is unbiased. Okay, but if the coin is biased, we will not be able to define the probabilities, or will not be able to tell the probability of head will be half and probability of tail will be half. Okay, so what are the way out? What are the way outs? In this scenario, we simply will be able to say that probability of head is P and probability of tail is 1 minus P. Keeping in mind the total probability law that P and 1 minus P, the sum total of P and 1 minus P equals to 1. So that P lies between 0 and 1. Okay. So this is the probability of head and tail when the coin is biased. Okay. Now, the fundamental question over here, actually what is happening here is that I told about this example in the beginning of my lectures, but probably you are not able to remember that. I discussed the same scenario in the beginning of my lecture. But again, I'm going to repeat the same thing. Okay, the fundamental question is how to judge that the coin is unbiased. What is the judgment? Or if I say that coin is unbiased coin and you put the values half and half, then how do I say that it is an unbiased coin? Have I measured everything regarding the coin? That is a very important question. Have I measured it? No, I cannot measure. Just like you, I also cannot. I cannot measure all the features of the coin because I do not know all the features of the unbiased coin. Okay, to me it is just a coin. As to you, okay, but I shall not also be able to say that it is an unbiased coin. But when the problem is given to you, I am saying that I'm declaring that it is an unbiased coin, and then only you are putting the values half and half. Now remember one thing, we do not actually calculate the probabilities, we actually thrust the value on the event. We put these values, okay, for unbiased scenario, we put these values for the biased scenario. Okay, so probabilities are actually not calculated, they are assumed. Now, since we are doing lots of problems on this particular situation, very basic situation, there needs to be some tool which will help me to say that the coin is unbiased. Okay, something is there which actually can help me to predict the coin is unbiased. Okay, so what is that way? So what is happening behind the screen is the following. At some point, some people are tossing the coin 100 times. 100 times, okay? And based upon this experiment, he is observing that he is getting the 50 times head and 50 times tail. And he is declaring that, yeah, I have done this experiment and therefore 50 heads occurred and 50 times tail occurred, and therefore the coin is unbiased with their chances. And then he is declaring that, yeah, the coin is unbiased. Another person, this is person one. Another person, person two, what he is doing at some other point of time, he is tossing the coin 1,000 times, observing head 500 times, okay, and tail 500 times. And he is saying that, okay, in his case also, the coin is unbiased coin. Okay, so what these people are doing, these people are saying that, okay, they are taking the coin and they are observing the coin tossing for 100 times and 1,000 times. And you know, in statistics, the experiment is synonymously known as the observation. So observing a coin for 1,000 times or 100 times or any other times, amount of time, that means we are doing the experiment with the coin with that many times. Experiment is equivalent to observation. Okay, so he is observing the experiment he's observing, doing the experiment 100 times means he's observing the scenario for 100 times. He's doing the experiment for 1,000 times, so that means he's doing the observation for 1,000 times. And then when he's after doing this experiment, he's placing the coin to you. He's declaring that, okay, this coin is unbiased. So basically what is happening is the following. He is based upon his assumption of the situation is based upon some sort of testing. His assumption that he has made regarding the coin is based upon some sort of testing. Okay, and after doing the testing, he is making the assumption that the coin is unbiased. Fine. Such an assumption, which is based upon this type of sample survey, such an assumption which is based upon observations is equal to, is known as, in statistics it is known as hypothesis. Hypothesis. So the person is making a sort of hypothesis over here that the coin is unbiased. But when he was doing the experiment with the coin for 100 times or 1,000 times or 10,000 times, getting equal number of heads and equal number of tails each time he tossed the coins, it may not happen that when the coin is coming to you and you are doing the experiment, you will be getting the same type of results that the person has got earlier. Because by the time he finishes his 1,000 times experiment, the coin will be hitting the floor many a times, and it has become the purity of the coin will be lost. It will lose many of its features. It is constantly hitting on the floor. It will be distorted in some way, which is also not visible through the naked eye, but it will be distorted, that we all believe. It will not remain as fresh as it was when the for the first time the coin was tossed. So it would be quite natural to assume that when I'll be doing the experiment with this assumed unbiased coin, I may not get the same type of results that the person who has given me the coin has got. Okay, so when the person is saying that the coin that he has given to me is an unbiased coin, he is making an hypothesis, kind of hypothesis. Here, assumption and hypothesis are synonymous to one another. Okay, but our job is to do a kind of testing this hypothesis. Testing this hypothesis. We need to test the hypothesis for its acceptance or for its rejection. So we have some basic tools by which a hypothesis about the situation can be tested, and this particular tool by which we do the thing is called test of hypothesis. Okay, so the chapter is called test of hypothesis. or sometimes it is also called a test of significance of the values that has been presented in front of you. Okay, so here I am going to start the topic of testing of hypothesis. And either after the testing, either I'm going to accept the hypothesis or I'm going to reject the hypothesis. That would be based upon the outcome of my experiment with the problem. Now, there are two types of hypothesis. One type is called the null hypothesis. It is denoted by 80. It is called null hypothesis. And another type of hypothesis is called the alternative hypothesis. It is denoted by H1. One of these hypotheses are complementary to one another. So if null hypothesis is true, then alternative hypothesis is false. If alternative hypothesis is true, then null hypothesis is false. So every null hypothesis will be associated with one alternative hypothesis. So if the person is saying that the coin is unbiased, and if this is his null hypothesis, then the complementary event to that, that is the coin is biased, is actually the alternative hypothesis. Okay, null hypothesis is actually known as hypothesis of no difference. Hypothesis of no difference. What does this mean? It simply means that if I do the experiment many a times, then the total amounts, the outcomes of the experiment will have equal chance of being selected. Okay, so there will be no difference between the probability associated with the outcomes. So such a hypothesis is actually called the null hypothesis. And whenever we test something in hypothesis testing, we actually test the null hypothesis, the acceptance or rejection of the null hypothesis. We focus on that. Okay, so we say that if null hypothesis is accepted, alternative hypothesis is automatically rejected. If null hypothesis is rejected, alternative hypothesis is automatically accepted. Okay, so this is all about. So the declaration of the coin to be unbiased, or the die to be unbiased, or a card to be a pack of unbiased cards, all these situations are actually based upon my sample survey, my observations, which I have performed many a times. And on the basis of that, I am putting the assumption in front of everyone. Okay, we do the once it is said, if I get the hypothesis that the coin is indeed unbiased, okay, if the hypothesis comes out to be true, then we say that the probability of head is, then we can say the probability of head will be half and probability of tail will be half. That means we are not calculating it. Actually, we are thrusting the value half to H and thrusting value half to T. That's what happens in this kind of thing. Okay, otherwise, be it biased, be it unbiased, pH equal to half and PT equals to half is a probability distribution. pH equal to P and PT equal to 1 minus P is also a kind of probability distribution. Okay, it is more general. So hypothesis testing is the objective of the entire course. So throughout the last few modules, that whatever we have learned actually will be used here and there in hypothesis testing. Okay, so hypothesis testing is actually very important topic, and it has many practical applications and real world. Okay, have you understood? You have any doubt? Now, let's begin with the problem first of all. So discussion of problem will make the thing very clear to you. So I always prefer to start with a problem. So my first problem of hypothesis testing is this. A dice is thrown 9,000 times. A dice is thrown 9,000 times. And a throw of 3 or 4 is observed 3 to 40 times. This is the situation. Can the die be considered an unbiased die? So this is the question that we'll be discussing here as our first problem. Can the die be considered an unbiased one? Okay. A die is thrown 9,000 times and a throw of 3 or 4 is observed 3 to 40 times. Can we consider that the die is unbiased? The situation is just the reverse of the situation that we usually do. Usually we are asked that, yeah, the die is unbiased. What is the probability that we'll get 3 or 4 if we repeat the experiment 9,000 times? We usually do this kind of problem. Now the problem, the way the problem has been put is just the reverse of our usual scenario. Now the situation is given to me and it is saying that you just decide on the situation, whether it is unbiased or biased. So it is kind of an inverse problem that we'll be doing over here. Okay. So we need to make some sort of hypothesis over here, first of all. So now you listen to me very carefully. In hypothesis testing problem, there are some protocols which need to be maintained. So one after another, I'm going to tell you the protocols that you must follow to do the hypothesis testing. First protocol is to set up the null hypothesis and an alternative hypothesis. So step number 1 is set a null hypothesis H0. I will write it as H0 because you know H0 stands for null hypothesis and H1 stands for alternative hypothesis. So we set a null hypothesis and an alternative hypothesis first of all. This is step number 1 in this type of problem. Okay. Since the null hypothesis is a hypothesis of no difference, you always remember this rule that whatever we write in the null hypothesis should be mathematical and should contain equality sign. Equality sign must be present over there. So if someone says writes in null hypothesis that okay, some say mean, he's talking about mean. So if he writes that the mean of the situation or mean of the system is less than or equal to some value, say 0.5, if he writes in this way, or suppose someone is writing that mean of the value is greater than or equal to 0.5, both of these persons are correct because they are including the equality symbol in the null hypothesis. If someone writes that mean of the situation is equal to 0.5, then also he is correct, because null hypothesis must contain in its mathematical expression the equality symbol. But if a person writes in null hypothesis that mean is greater than 0.5, or if he writes mean is less than 0.5, then he will not be able to perform anything because he has not considered the equality symbol in the null hypothesis. Because after all, after setting the null hypothesis, we need to have some kind of tool where we'll be putting the values, and if we do not include the equality symbol in the null hypothesis, will not be able to apply the formula, because the formula tests the null hypothesis. We assume we consider the formula under the assumption that the null hypothesis is true. Okay, so this is correct, but this part of this type of thing that we are, if we write, that is wrong. Okay, equality symbol must be present in null hypothesis. That is the catch. So in this situation, we are going to set our null hypothesis. So what will be our null hypothesis? Null hypothesis will be denoted by H0 and alternative hypothesis will be denoted by H1. And both of these are actually statements. Null hypothesis is a statement. Alternative hypothesis is a statement. And statement cannot be, if you write a statement, you cannot put equality symbol. You cannot put equality symbol. You cannot write that H, if you consider H naught to be a statement, you cannot write H naught is something. This is wrong. This is wrong. Rather, you have to put a colon over there. Whenever we make a statement, we put a colon over there. So this colon has a significance. You just don't think that I have put it and you can put any symbol over there. It's a statement, remember. This is also a statement. These are some basic rules that you need to follow over here. Now, what is the statement? What I'm testing over here? I'm testing the die. We are interested in finding whether die is unbiased or not. Okay. First of all, suppose the die is unbiased. Suppose the die is unbiased. Die is unbiased. If the die is unbiased, then what happens? Each face will be given equal amount of probability, and we all know that what that value is. That value is 1 by 6, 1 upon 6. Now, here the event that we are interested in is this event, a throw of 3 or 4. So if someone asks that what is the probability that when a die is, an unbiased die is thrown, a simple question, if an unbiased die is thrown, what is the probability of getting 3 or 4? You will immediately say the probability of getting 3 or 4 is as follows. This singleton set 3 is an event, the singleton set 4 is an event, and if you know that these events are mutually exclusive, you will write that this is equal to probability of 3, okay, plus probability of 4. We all know this by the basic axiom of the probability. These are mutually exclusive. And since probability of 3 is 1 by 6 and probability of 4 is 1 by 6, so immediately we can say that for unbiased die, the probability of getting 3 or 4 will be 2 by 6, which is 1 upon 3. Okay, so this is our some kind of rough work that we have done in our mind. Now in the hypothesis testing, we are going to assume that the die is unbiased. If the die is unbiased, that is our assumption, then we'll be able to put this particular probability in the formula that we'll be considering over here. So if the die is unbiased, and since H1 is the complementary to H0, so automatically in H1 we'll write die is biased. Okay, but as I said that null hypothesis should contain some kind of mathematical symbols, so writing them just by the statements will not do the job. So we need some sort of mathematical statement over here, which we'll put in the respective formula that we'll be considering. Fine. Now you know that here in this particular problem, the success, if this is our experiment, the success is denoted by the condition that 3 or 4 will occur. This is our success. Okay, and that the probability that we have calculated over here is the probability of success. Actually, the probability that we have calculated is called the probability of success, which we have calculated as 1/3. And if we consider the probability of success to be capital P, then we'll say that if the die is unbiased, P equals to 1/3. Okay. Now, to write the mathematical statement of the null hypothesis, what we can do is that we consider the probability of success over here. We can write the probability of success, which we denote by probability P, and we'll say that it is equal to 1/3. Okay, this rough calculation that I am doing, it is not rough in the sense that this particular part should not be shown in the calculation. You can divide your copy into 2 halves. The right part of the copy, you can show the calculation to the examiner that you are doing. I'm not talking about the online examination. This is also the green colored portion is also a part of the problem. How have you found the probability of success to be 1/3? This is the calculation. Okay. And you see, if I do so, the equality symbol is actually appearing in the null hypothesis, which is quite expected. And consequently, in the alternative hypothesis, we are writing the probability of failure in the following manner, which is equivalent to P not equals to 1/3. What would be the probability of failure? I'm not interested in that, but it is, at least we can say that, this should not be equal to 1/3. Now, either this is right, either H0 is right or H1 is right, that we do not know, and that we want to test in hypothesis testing. So this situation needs to be tested. This is our step number 1. Our step number 2 talks about a mathematical tool. So if this is the situation, what is the mathematical tool that we'll be introducing over here? What is the mathematical tool? Mathematical, or rather we must say statistical tool that we'll be implementing over here, because we need some sort of formula. So what is that in this particular situation? So what does statisticians do after getting this type of problem? They actually try to identify the situation. So they identify the situation. Identifying the situation means they are trying to get an idea about what sort of probability distribution this situation must follow or can follow. Okay. And you see that in this situation, number of times the experiment is getting repeated. It is given over here, it is 9,000, and success is there. Probability of success is also present. The situation is a kind of binomial situation. And in hypothesis testing, we'll not be applying the binomial probability law over here, but we'll be applying the probability binomial approximation to normal distribution. In this particular case, the tool that we'll be applying over here is binomial approximation to the normal distribution. We know about the normal distribution. How does it look like? The standard normal variable looks like x minus mu by sigma. We all know that. But since the situation is behaving more or less similar to binomial distribution, so in case of mu, you can put NP, and in place of sigma, you can put root over NPQ, because in binomial distribution, the mean of the random variable is NP, and the variance of the random variable is NPQ. So the formula that we'll be using over here is as follows. We'll write, in step number 2, we'll write under the null hypothesis. This statement is very important, so I'm red marking it. Under the null hypothesis means considering the null hypothesis to be true, we are going to apply the formula capital Z, a standard normal variable, where this is given by x minus mu by sigma type of formula, where mu is number of times the experiment is performed multiplied by the probability of success divided by under square root sign n capital P probability of success into 1 minus capital P. Okay. Now you see what I told. I told you earlier that in null hypothesis, cannot consider, you have to consider equality symbol. Okay. If equality symbol is missing in null hypothesis, then you will not be able to perform the test. Now you see, try to connect what I said regarding null hypothesis and to this particular formula. In the formula, capital P is present. Now suppose you interchange the situation. In H0 you write P not equals to 1/3, and in H1 you write P equals to 1/3. And since the null hypothesis, since the statistical tool is based upon the null hypothesis, it is not dependent upon the alternative hypothesis. So if you do not include P equals to 1/3 in null hypothesis, you will not be substitute the value into the formula. So appearance of equality sign in null hypothesis and the formula, they actually are interconnected to one another. And therefore, I said the null hypothesis must contain the equality sign. What is X over here? X is the number of times success is observed. Number of times success is observed. What is P? Probability of success. What is N? Number of observation. Number of observation. Okay. And such type of thing that we have used over here, this formula that we have used, this follows a normal distribution with mean 0 and variance 1, because you know it is the formula for the standard normal variate. So this is our step number 2. In step number 3, we need to do the calculation. It is all about calculation. So we are going to put the values. So x minus np by root over npq, the positive square root of npq. This means x is 3240 times the success is observed. Number of observation is 9,000. Probability of success is 1/3 that we have considered over here. And here also we are going to put the values 1/3 and 2/3. Okay, under the square root sign. Can you tell me please, Ritika or Ritika, what would be the value of this quantity? Can you just quickly do the calculation and tell me what would be the value of this? Because again, I do not have the calculator with me right now. This would be 3240 minus 3,000. And that would be 3,000. Okay, that would be root over 2,000. So what is this value? 240 divided by root over 2,000. Can you tell me the value? Can you write it in the chat box?
$5.366.
5.366. 5.366 approximately. The second part, though the third part is complete. We have done the calculation. Step number 4 tells us about how to write the conclusion. How to write the conclusion. Now, quickly I'm saying, because the time is running out. First, conclusion, drawing conclusion has several parts, subparts. Part 1 says that if modulus of z, absolute value of z is greater than 3, you reject your null hypothesis. In our case, you see our mod z is also 5.366, and therefore it is greater than 3, and therefore we reject 80, and the final conclusion is die is biased. So this die we cannot